This video is over lesson 39, excuse me, circumference of a circle, and it's for my pre-algebra classes. So ladies and gentlemen, if I were to ask you to identify a circle, I'm sure you'd have no problem doing that. But then if I were to ask you to define a circle, what makes a circle a circle? This is something that I think you'd have a much harder time doing. So take a moment, pause the video, and think for a second, what makes a circle a circle? All right, now likely you came up with ideas like it having no straight sides or having one rounded side. Things like that typically come up. But a lot of our descriptions can either describe ovals or even irregular shapes, irregular curvy shapes. So a circle has a very specific definition, and it's actually the set or group or collection of all points. So every point on here, it's just a collection of points on a plane. And to say on a plane just means that it's flat. That are equidistant. And equidistant means exactly what it sounds like. Equal distance. Equidistant from a center point. So you've got the center, and if this is a true circle, then every point on the circle is the same distance from that center. Now, the on a plane makes a difference, because if I just say the set of all points that are equidistant from the center point, and I don't say on a plane, then while working in three-dimensional space, you'd actually end up with a sphere. So we got to say on a plane just to make sure it stays on there. Now, working with circles, we've been working with circles for years now. There are several special measurements on a circle that we need to be aware of. So one of the simplest is just to go from the center out to the circle. And so from the center out to the circle itself, this is called a radius. R-A-D-I-U-S, radius. Okay. Another measurement that we don't talk about as often, this comes up more in geometry than it does in elementary school or middle school math. And it's anytime we make a segment that starts on the circle and ends on the circle. So this is what's called a chord. And there are many different chords around the circle. So this one I just started here and ended there. I could start here and end there. I could start here and end there. I could start here and end there. Those would all be chords. I could start somewhere else. As long as it starts and ends on the circle, that's a chord. Now, among the chords, there's one chord that's particularly, sorry, I want to backtrack here. Sorry, I forgot for the radius. Real quick here. Let's say you have one radius, and you put that together with a second radius. You would say that we have two, not radiuses, but radii. Sorry about that, I forgot to mention that. So the plural of radius is radii. Okay, so back to the chords. So among the chords can get smaller and smaller and smaller. There's actually no limit to how small they can get, because all I got to do is take these two endpoints and get them closer and closer and closer together, and they'll make smaller and smaller segments. However, every circle has a maximum chord, a biggest chord possible. And that is going to be the chord that goes across the circle through the center. And because that's a special chord, it gets a special name. I'm going to flip my paper upside down here so I can write along the bottom of this line. This special chord, the largest chord of the circle, is called the diameter. D-I-A-M-E-T-E-R. diameter. And the diameter, if we look at it, if we go from the center to there, that's actually a radius. If we go from the center in the other direction, there's another radius. So it turns out that 2 radii is also 1 diameter. Now, symbolically, we often say that the radius is lowercase r. We often say that the diameter is lowercase d. So in this case, we're saying that 2r equals 1d, which is just d. Now, among circles, there's at least one more measurement that we need to take into account. At least for this lesson, one more we need to take into account, and that is the circle itself. So if we measure the distance from here to here, that's the radius. The distance from there to there, that's the diameter. Distance from there to there, that's at least one of the many chords. But what about the distance of the circle itself, the distance around the circle? Well, that, of course, is the title of our lesson. That is the circumference. I'm going to try to write that around the circle here and just so the distance around the figure is the circumference itself. And then symbolically, circumference, well, it's going to be c for circumference. However, because circumference is actually a perimeter, so this is going to be the distance around a figure is a perimeter. So this is just a special name for the perimeter of a circle. And if we think back to when we've done perimeter in the past, remember that in our formulas, anytime there's something that we calculate like perimeters, areas, volumes, those get capital letters. So circumference is actually going to get a capital C. Now, every circle, every true circle, has the exact same shape. So because of this, for every circle, the ratio of circumference to diameter is always the same. So if you take the circumference of one circle and make a ratio with the diameter from that one circle, so C sub 1, D sub 1 come from the same circle, it's going to be equal to the circumference from a second circle compared to the diameter of that second circle. And in fact, we could keep doing this. It'll be equal to the circumference of a third circle compared to the diameter of that third circle. And on and on and on forever. And in mathematics, when we get a situation like this where we keep getting the same ratio over and over and over again, that means that this is going to be one set number. And so we want to know what that number is going to be. And you probably already have a good idea what that number is going to be. So go ahead and say it if you know it. And hopefully what you just said was pi. So there's our pi symbol. So pi is a Greek letter. So in English, we would look at this as pi, pi. But it's just the Greek letter there. Now, something that we should already know about pi is that pi is an irrational number, which means there is no way to write this as a fraction using integers, at least not exactly. So the reality of irrational numbers is in order to use them, in order for them to actually be helpful, they always have to be rounded. They either have to or be used symbolically. So either we need to use the pi symbol and keep it, or we need to replace the pi symbol with something that it's approximately equal to. So pi has a couple of standard approximations. So probably the most common approximation for pi is 3.14. And that's the one that I want you to use unless there's something that would basically say otherwise. Another one that's probably the second most popular is 22 sevenths. And now remember I said just a second ago that pi cannot be written as a fraction using integers, but then here we have a fraction using integers. Now the reason why this is okay though is because we're not saying that they are truly equal, because they're not truly equal. They're close, but not equal. Now 22 sevenths, why does 22 sevenths work out? If we take a look at 22 sevenths for just a second, that's an improper fraction. If we change it back into a mixed number, 7 goes into 22 3 times with 1 left over. So 3 and 1/7. And then if we remember from a previous lesson, 1/7 has a nice little pattern, if you can remember it. 1 4, double that, 2 8, double that, 5 6, but we're not going to do a 6, it's actually going to bump up to a 7. Repeating. And so 22 sevenths is really 3.142857 repeating. Well, if you were to round this off then to the nearest hundredth, 3.14. So they're both actually pretty close to each other. So 22 sevenths is actually a little bit bigger because it's got all this repeating stuff than just 3.14. But they're both pretty close to each other and they're pretty close to pi. So one's a little less, one's a little more. So ladies and gentlemen, with this in mind, we're going to do a little bit of algebra here. So we now know that for any circle, the circumference divided by its diameter, so that ratio, equals pi. That's always true for any circle. So I want a formula for circumference. That is the title of the lesson, circumference of a circle. So right now we're taking the circumference and we're dividing by d. So if we do the inverse of that, we're going to multiply both sides by d. So multiplying by d will cancel out the d's there. The d that I'm multiplying by will cancel with the one I'm dividing by. And that leaves me with just c. And I'm going to skip a line that I wouldn't normally skip here. And then on the other side, we're going to end up with this pi times d. So pi d. And at this point, go ahead and grab your highlighter. I don't really care what color you choose. I've chosen blue. I just want to put a box around this to make that pop out. Now, we're going to take this now and do a little bit more algebra. So c equals pi d. Now, remember up top, we said that 2r equals d. This means anytime you see d, you could replace it with 2r. So down here, I'm going to rewrite this now, but I'm going to replace d with 2r. So in algebra, we call that substitution. We're going to substitute 2r for d. Now, you might be tempted to just leave this here, but in algebra, we typically have a particular order that we put our factors in. So within a term, there is an order that we have. And so we're going to just write that order down here because it's going to be important here in a second too. So the very first thing we always put is numeric constants. So that's always the first thing in the term. So I'm going to put my c equals, and I do have a numeric constant, and that's this 2. So numeric constants are just numbers, plain old numbers. They always go first. After symbolic or numeric constants are symbolic constants. So just as numeric should have made you think of number, symbolic should make you think of symbols. So a symbolic constant is just a symbol that represents a constant. So it's not just a plain old number, but it's a symbol that represents a constant. So in this case, pi would be a symbolic constant. If you think about the numbers that you learned way back in elementary school, pi was not one of those numbers. You know, when you learned to count 1, 2, 3, 4, 5, 6, even when you learned fractions and decimals, pi is irrational. It wasn't one of the ones you learned. We can't write it normally, so we use a symbol to represent it. After our symbolic constants, next come variables. So in this case, because we're moving from circle to circle to circle to circle, the radius can keep changing. So the radius is going to vary with each circle. So the radius there would be my variable. And now we don't have this here, but I'm just going to put it in for your knowledge sake. But after that would come functions. And so you're going to see that more in later classes. But functions would include things like square roots. Eventually get into a thing called trigonometry, where we'll talk about sines and cosines and tangents. In Algebra 2, you'll start talking about logarithms. So those are the things that are going to be functions. And they usually go after our variable then. And then finally, hanging out after all that is our units. So that is the typical order of things for a final answer. So with that being said, grab another highlighter here. We have a second formula now for circumference. And the only difference between these two, really, is that one uses d to find the circumference, and the other uses r to find the circumference. That's really the big difference. So I know there's a 2 there, but the important part is this uses diameter, this uses radius. So let's flip to the back, and we're going to do a few examples here. So I'm going to draw a circle. I'm going to put a center dot in there, and then I'm going to go like this and label that as 6 inches. And I would like to find the circumference of this. So first thing we need to think is, what is this? So what kind of a measurement is this? Well, since it goes from the center to the circle, this is a radius. So this diagram, this picture, is showing us that the radius is 6 inches. So if it's the radius, then it probably makes more sense to use the formula c equals 2 pi r. Now, strictly speaking, do we have to? No. You could convert the radius into a diameter, and then you could use the diameter to find the circumference using the other formula. But why bother? Why not just do this? And to be honest with you, as you start getting towards high school, this is actually the formula that you're going to start leaning more and more towards. There are other formulas that also use radius, but not very many formulas use diameters. So typically it's the radius we really want to know when it comes to a circle. So we're going to go ahead and do this. So c equals 2 pi r. So first thing we see in the formula here after the equal sign is 2. Then we see pi. And then r, so times r. R in this case is 6 inches. And now if we go ahead and multiply and put things, remember, in this order. Okay, so first is going to be the numeric constants. So the 2 times the 6 will give me a 12. And then symbolic constants come next. So I have the pi. And, well, that's the 2, the pi, the 6. The only thing left is inches. So the circumference of this circle is 12 pi inches. Now, you may be thinking that I made a mistake. I did not. What we have here is the exact answer. The exact answer is 12 pi inches. Now remember, ladies and gentlemen, that when we're using irrational numbers, we can only use them symbolically. Now this may not be a very helpful answer. For example, if you had a circle with a 6-inch radius and you were going to put a length of string around it and you wanted to know about how much string you needed to go around this circle, 12 pi inches is probably not going to be terribly helpful. But it's true. Now, one of the advantages of having an answer like this, especially if you think about passing that off to other people, is this then allows somebody else to come along and decide where they want to round to. So where do they want to round to? So they could round to the typical 3.14. Maybe somebody else, because of whatever they're doing, they really don't need a very exact answer. So maybe they just round pi off to 3. Or maybe you're working in a company where you've got another department that needs this to be super, super accurate. And so they round pi off to 3.14159. So an exact answer like this, one of the benefits is you can hand that off to someone else and then they can decide how far to round off pi to and finish off the problem. Another advantage to this we're going to see in a little bit is that when we're working with this and we have this symbol in here, especially when we're doing other calculations as well, sometimes we can run into a situation where by leaving this symbolically as pi, it can cancel out with another pi somewhere else. And we'll see that at the end of the lesson here today. So now, like I said, this is not a terribly helpful answer. So you're only going to do this, give the exact answer if the book asks for the exact answer, or if it says in terms of pi. In terms of pi would mean give it with the pi symbol still there. Okay, so if it doesn't say that, then we are going to approximate pi. And again, typically we're going to use 3.14. So if I use 3.14, here's the thing though. Pi is not exactly 3.14. So I would need to change this to an approximately equal to if I'm going to make pi 3.14. Because it's no longer exactly equal. It's close. It's close enough that the answer will work, but it's not exactly equal. So there's my 2, there's my pi approximately, and then my radius is still 6 inches. And then from here, if we go ahead and we multiply that together, 2 times 3.14 times 6 comes out as 37.68. And of course, it's still inches. So because we use that approximately 3.14, this is only a rounded answer. It's close, but it's not exactly correct. Okay. So unless the book tells you otherwise, give it in rounded answers. The rounded answer here is better because of that irrational pi. All right, let's take a look at another example. So new circle here, I'm going to put my center in. This time I'm going to draw a segment right like that. And once again, I'm going to label it as 6 inches. So when you see this, we see that we're going from circle to circle through the center. So this is the longest chord of the circle, this is the diameter. So diameter equals 6 inches. So if diameter equals 6 inches, then it makes more sense to use the formula with diameter in it. So once again, I'm going to find the exact answer to start. So I'm going to leave pi as pi, but then I'm going to multiply that with the diameter, 6 inches. Remember your order, so numeric constants first, 6. Symbolic constants second, pi. We don't have a variable, we don't have a function, but we do have the units, inches. So the circumference of this one is 6 pi inches. Now if we find the, remember that's the exact answer. We'll just say exact this time. Now let's find the rounded answer, the one that you're going to find if you're not given instructions. Remember, only if you're given instructions to find the exact answer or in terms of pi. So in all of the circumstances, we're going to replace pi typically with 3.14 and then times the diameter, which is 6 inches. And now if we go ahead and multiply that together, we get 18.84 and inches. So that's right there is what you're going to do unless you're given other instructions. All right, we're going to make another circle. For this one, I'm going to make a segment going right like that. And I'm going to label this as 14 centimeters. So since this goes from the center to the circle, that means it's a radius. So I'm going to gravitate towards 2 pi r for my circumference. Now we're going to skip the exact answer this time. That's pretty easy. Hopefully you've got the hang of that. We're going to go to the rounded answer here. So pi, or c, is approximately equal to 2 times. Now here, this is a time because 14 is divisible by 7. So pi approximately equal to 22 sevenths, because fractions mean division, so that's basically dividing by 7 there. So pi approximately equal to 22 divided by 7 may be a good idea. So this would be a time where you might want to consider using 22 sevenths. So if I use 22 sevenths here for my pi, then I just need to multiply by r. So r is 14 centimeters. Now, when I look at this problem here, if I just look at the numbers for a second, I have 2 times 22 sevenths times 14. Those are my numbers. Well, remember, ladies and gentlemen, that whole numbers are really just themselves over 1. So this is really 2 over 1 times 22 sevenths times 14 over 1. So one of the shortcuts that I'd like you to recognize here is that when you have a whole number, the whole number is really like a numerator. It's just a numerator over 1. So that means that denominators can reduce with whole numbers. So down here, what I'm going to do is I'm going to reduce this 7 denominator with this whole number 14. So 7 goes into itself once, 7 goes into that 14 2 times, and so now I've got 22 over 1, so this is really just 22. So 2 times 22 times 2 again is 88. And the units are centimeters. So by using the 22 sevenths, when you have a radius or a diameter that are divisible by 7, can allow you to get nice whole number answers, rounded answers. All right. Which brings us to the last problem of our notes. And what I need you to do for me now is I need you to make a circle that's 4 spaces big. 4 spaces big. And then what we're going to do is we're going to put a center dot in there. And then we're going to make a circle on the inside that's 2 spaces big. And so they share the same center. Now this isn't one of our vocab terms for this lesson, but just for your knowledge, these would be called concentric circles. They have the same center, so they'd be concentric circles. So if I were to draw a segment from here to here and label that as R, and then draw a segment from here to here, because I mean that's the radius, right? But from here to here, this is another radius, so if I labeled this as R as well, we run in the trouble of these are 2 different things, they're going to have 2 different numbers. This doesn't really work. And so one of the things that we can do is we can use subscripts to label which radius we're talking about. So here I have a large circle and I have a smaller circle. So what I'm going to do is on the smaller radius, I'm going to put a S. So that's going to be R sub S. And then on the larger circle, I'm going to put a subscript of capital L. Capital L for the large radius. So R sub capital L is my larger radius, R sub S is my smaller radius. And you can see just from the way that we drew this that the radius here of the big guy is twice as big as the little guy. So the larger radius equals 2 of the small radius. And so that's going to be important here in a second. So one of the things that we may be asked from time to time is to compare one figure to another figure, or an aspect of one figure to an aspect of another figure. So in this case, we might be asked to compare the circumferences of these two circles. So if I wanted to make a ratio out of that, I might say the larger circumference compared to the smaller circumference. Now, if we want to simplify this and see, what is this ratio here of their circumferences, let's go ahead and then apply what we know. So I know that circumference is, in this case, because we have r, 2 pi r. So for the larger circle, that's going to be 2 pi, and then its radius is r sub l. Now for the smaller circle, its circumference is also going to be 2 pi, but its radius is the small r, r sub s. Now if we take a look at these two here, this is where I was talking about earlier. By writing this pi symbolically, okay, they can just cancel out. We can just use our algebra to cancel them out. Now we don't have to worry about rounding those off to anything. They're just gone. They're ones now. For that matter, my 2's will also reduce down to 1's. And so the ratio of the circumferences will actually equal the ratio of the radiuses. The radii, excuse me. The ratio of the circumferences equals the ratio of the radii. Now, using what we know up here, though, I know that r sub l is 2 of r sub s. So I'm going to replace that. I'm going to use that thing that I know, that the larger radius is twice as big as the smaller radius. And now we end up with a new ratio where we have r sub s and r sub s. So those will reduce down to 1's, and they're gone, which means that if I finish this off, 2 times 1 is 2, and then on the bottom we just have a 1. So what is the ratio of the circumference of the larger circle to the smaller circle? 2 to 1. And that, ladies and gentlemen, is the end of our lesson.